So to begin with Calculus 2, we're going to talk about what integration is. And the easiest way to talk about what integration is to start with the area and distance problems. So what we're trying to do in integration is we're trying to find the area. We're trying to find the area underneath. Wait, hold on. I have a little. Yeah, we're trying to find the area underneath this curve. So we're looking for the area in S. Now, if I have a rectangle, we know how to find the area. If I have a rectangular shape, and let's say the width is 3, the length is 10, we know what the area is. We simply take 10 multiplied by 3. But when I have an irregular shape, the method to calculate the area is a little bit different. Now, before we go through the steps, let me sort of tell you what we are trying to do today. What we're trying to do today is we're trying to kind of go backwards. Okay, we're kind of doing the same thing as what we did in differentiation before, but we're going to do it with integration. And one of the things that you learn at the very beginning of integration, at the very beginning of differentiation, is you learn that the derivative is the slope of the tangent. So we ask you this question of, hey, we need to find the slope here, and we call this f prime at A. Right? We're trying to find the slope here. We're trying to find the derivative here. And for us to do that, we did a few things at the beginning. And one of the things that we did was we tried to tell you that we can't really find the slope unless I have 2 points, right? So unless we have 2 points. So we needed 2 points for us to find the slope. We needed a point here, and we need to pick another one sort of up there. But of course, this result over here is just an estimate. It's not the actual slope of the tangent line. So what we did was we did something else. And we did something like this. We took our second point, which in this case, we have 1 point here, and we took a second point here, and we realized that, the line, the secant line that we draw is not very good. It's not very accurate. So we decided to not do this. We decided to make the second point closer, right? And we back it up and closer, and we back it up closer. And eventually, if I make the distance between the 2 points 0, if I make it as close as we can, if I make these 2 points with distance of 0, if I do the limit, then we get the exact value of the slope of the tangent line. And that's what we did. So today we're going to do the same thing. We're going to do the same thing with integral. But if you think back to how we learned this process, you'll notice that the only time we ever do this on the test, the only time when we ever do this on the test is usually on your first midterm, sometimes on your final exam, and we ask you to find the derivative using the definition, all right, using the limit definition of the derivative. And that's the only time that we are ever going to do the limit. Most of the time when we find the derivative, right, when I have a function like this, when I try to find the derivative f prime of 3, for example, what I will do is I'll just find the derivative. I'll use some rule, right? I'll use the derivative rule, x squared, the derivative is 2x. So we will later on have some shortcuts. But on your first midterm, there may be questions that look like this, that you have done, where it forces you to answer it using the definition of the limit. So today we're going to do the same thing, but with area. So instead of doing slope, today we're going to do area. All right, now that we gave you a overview of what's going to happen, now let's go back to our area problem. So what we are going to do to calculate the area here is we're going to realize that we can find the area of a rectangle, right? And if I ask you, if I have a rectangle like this, 3 and 10, how do we know that the area is 3 times 10? If you think back to your elementary days, you might have toys that look like this, right? Strips that have 10 little bars, and then something like this, something that looks like a piece of chocolate. And you'll say, oh yeah, in the first column, they are 3. In the second column, they are 3. And there are 10 columns in total. I'm missing one here. There are 10 columns in total. So in total, it's 30, right? 3 times 10. We're going to do the same thing here, but with an irregular shape, with an irregular curve, we're going to pretend that we have little rectangles that look like this. We're going to pretend that we have little rectangles, and we're going to add up all the little rectangles. And we're going to use that to calculate the area. So let's do an example. We're going to try to estimate the area under the parabola y equal to x squared. And we're going to do this from 0 to 1. So this is my parabola. And from 0 to 1, 0 is here, 1 is here. What we're going to do is we're going to find this area, this S area over here. So all this region in here. And the questions that we are going to ask you are going to have a little bit more information from than this. We'll tell you how many rectangle we would like to cut it up into. So in this example, we're going to cut our area into 4 pieces. So you can see over here, 1, 2, 3, 4. And the 4th piece will look something like that, right? The 4th piece will look something like this. But of course, we can't really find the area of each of these little pieces because once again, this is a strange shape. So what we are going to do is we're going to try to make them look like a rectangle. And we're going to accept that that's not the right answer right now. So what we're going to do is instead of drawing it like this, we're going to say, let's use the right endpoint. So we're going to, for this little bar that goes from here, so that goes from 3/4 to 1, we're going to use the height, the y value at 1. We're going to use the y value at 1. So we're going to say that the height over here is 1. So this height from the bottom to the top, this height over here, oops, it's a little bit hard to use the mouse. Yeah. So the height over here is 1. We're going to draw a rectangle like this. And the rectangle, the height of the rectangle is going to be dependent on where the right-hand side is in this example, where the right-hand side is. Okay. And so if we are to do that, if we were to use the right endpoint, so we call this the right endpoint. And if we use the right endpoint in this particular case, for the 4 rectangles that we have, well, when I have the 4 rectangles, for the one on the for the first one on the for the one to the right, okay, for this one over here, the y value that we're the x value that we're going to put in is 1. We're going to put in this 1. And the y value, the height, is going to be 1 squared. Why is it going to be 1 squared? Because my function is x squared, right? My function is x squared. So whatever my x value is, in this case, the x value is 1. To find the y value, to find the height over here, I'm going to square it. So that's 1 squared. So I use the 1, I square it out, that gives me the height. Now, if I talk about the first rectangle that we see over here, now notice the first rectangle, I'm going to use this point on the right-hand side. I'm going to use the right end point. The right endpoint in this case for the first rectangle is a quarter. It's a quarter. And the height in this case is a quarter square. Right? Because the y value up here, it's not a quarter, it's a quarter square. And this is y is equal to x squared. So we're going to do that. Now, each of these rectangle, the width at the bottom, so the width at the bottom over here, so each of the rectangle has a width of 1/4. And it has a width of 1/4 because we are starting from 0 and we go up to 1 and we divide it into 4 pieces. So from 0 to 1, divided into 4 pieces, that's 1 divided by 4. Right? So that's how I find the width. And you'll notice that for us to find the area of each of these little rectangle, I'm going to take the width, 1/4 in this case, multiply by the height, and the height will be the y value. So the height will be the y value here, and for the second rectangle over here, third rectangle over here, and for the fourth rectangle up on the top. To calculate the value, we will square each of the x value, x coordinate, to find the y coordinate. This is how we find the area. And at the end, the area is, I can't see. Okay. The area is 0.46875. Okay, so 15/32. So that's the area. What you'll notice is that each of these rectangles is actually bigger than the strip, right? So if you look at the this area over here, so if you look at my rectangle, it's going to be bigger than this particular strip. So our real area is going to be smaller than that. And this particular case is true because our function is increasing, our function is getting bigger, and I'm using the right endpoint, which happened to be the highest point of each of these rectangles. This part is not very important. But occasionally, just like when we might ask you to find the derivative using the limit at a specific point, occasionally we'll ask you to calculate these sums, and these sums has a special name called Riemann sum, and we'll tell you how many rectangles do we want to break it down into, and we're going to ask you to find the area. So we're going to ask you to do that. What we can ask you to do right now is to find the area of the same parabola using the same 4 rectangles. Well, using 4 rectangles, but this time the 4 rectangle is going to be different. If we use the left endpoints, then our rectangle is going to look a little bit different because in the example before, we look at the right endpoints. So in this example over here, we're going to use the left endpoint. So we're going to do the left endpoint from 0 to 1/4. From 0 to 1/4, we're going to use the left-hand side. So my rectangle is like that, which has an area of 0, right? Here, the area is 0 because my height is 0. For the second rectangle, I'm going from 1/4 to 1/2, but I'm going to take the left-hand side. So I'm going to take the left-hand side. So I'm going to go up to 1/4. I'm going to hit the line, hit the curve, and this is the rectangle that I'm going to make. The height in this case for this particular rectangle over here is going to be 1/4 square. So I'm going to do that. And I'm going to do that for every single rectangle. And in this case, we're only going to get 7 out of 32. So we can see that the real area should be somewhere in between, right? Bigger than the 7/32, but smaller than the one that we just found. Okay, next. what we sort of realize is that now we have sort of established, now we have shown you a way to calculate area. Now this way is not very accurate, right? And it's just like when we are trying to find the slope of the tangent line, we say, hey, remember in high school we pick another point and we try to and then we can connect them as a straight line. We call that the secant line, and we can calculate the slope here. And of course, you can say, yes, we can do that, but that's not the right answer. The right answer should be something like that, like the blue one. And this is what we have done so far. We have done something that's really, that's an estimate, like the secant line over here, like the slope of the secant line. And now we're going to turn that into the real answer. And for us to turn that into the real answer, we're going to do some limits. And of course, we learned limits before, so we don't have to spend 2 or 3 weeks teaching you limits. And so here, this is the limit. We're going to ask you to show that the real answer, the real area, is going to be about 1/3. So the real area is going to be about 1/3. So you notice what we have done before. Before we have gotten two numbers using the two different endpoints, the right-hand side, the left-hand side. And we found that it's somewhere between 0.2 and 0.446. Now we're telling you that the real answer is 1/3, 0.333. I'll repeat. Yeah. And so we're going to show you how to do that, because that's the step to get to our answer. So what we're going to do is, oh, by the way, you should realize at this point, if I cut my area into more rectangle, so in this case, I cut my area into 2, 4, 6, 8, 10, 12, 14, 15. Okay, in this case, I cut my area into 15 rectangles instead of just 4. And you'll notice that if I add up all the area here, this result, right, will be better than that one, right? And it will be better than this one where it's a lot bigger. Why? The reason is because I have more rectangles, right? I have more rectangles, and I'm finding the height more accurately each time because I have more rectangles. So what we're going to do is do this. Let's imagine I have n number of rectangles. Let's imagine we can have any number of rectangles we want. And what we're going to do eventually is, instead of shrinking the distance of 2 points down to 0, we're going to make the number of rectangles as big as we can. We're going to make the number of rectangles infinite. So if I have many rectangles, my answer is going to be very, 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 very good. And it's going to be the perfect answer. And that's what we're going to do. If there are n rectangles, each of the rectangle will have the width of 1 divided by n. Now, we have the 1 on top because we started from 0, we go up to 1. So I will find that the total interval is 1 minus 0, right? The interval here is 1. And so that's why I use the 1 here. The distance here is 1. If I'm going from 0 to 2, I will have a width of 2 divided by n. If I'm going from 3 up to 8, then the width will be 5 over n, right? So this is the process. We're going to find the width of each of the rectangles first. Now, once I find each of the rectangles, we're going to, each of the width, we're going to now find the right endpoint and use the right endpoint to find the height. Now, we don't have to use the right endpoint. It just so happened that the right endpoint is the easiest one to use. And I'll tell you why. So it turns out the right endpoint is the easiest one to use. We can use the right endpoint, the left endpoint, somewhere in the middle, anywhere in the middle. It doesn't matter. They will all give you the same answer because we're going to we're going to make the number of rectangle very big, and each of the rectangle is going to be very small. And the width is going to be super small, that the right-hand side, left-hand side, in the middle doesn't matter. But it's easiest to do the right-hand side. It's easiest to do the right-hand side because normally this is what we do. You'll notice that if I divide when I divide the rectangle into 4 pieces, there are going to be 5 interesting points, right? 1, 2, 3, 4, 5. Now, of course, if I'm using the left endpoint, I'm going to use these 4. If I'm using the right endpoint, I'm going to use those 4. But they are 5 points in total. By convention, we like to call this one the zeros point, the first point, the second point, the third point, the fourth point. And the reason why we do that is because if each of the rectangle has a width of 1/4, then of course this one over here is at a location of 1/4, right, times 4. And this one is 3/4, it's 3 times 1/4. Right, and this one is 2 times 1/4. Okay, and this one is 1 times 1/4. And this one is, of course, 0 times 1/4. Okay. So this is the reason why we name them point number 0, point number 1, point number 3, 2, point number 3, number 4. They are 4 rectangles, and they are 5 points, 0 to 4. Now, because they are 4 rectangles, it's easiest to count 1, 2, 3, 4 like this, right? It's easiest to count the points 1, 2, 3, 4. That's how we count. We start from 1, not from 0, most of the time. And you'll notice that in this case, they happen to be the right endpoint. So this is why we normally use the right endpoints in our definition. And it's the easiest one to do. It doesn't matter when you're doing it yourself, but most of the time we use the right endpoint. In this case, because I have 1/n as the width, then the endpoints are 1 times 1/n, 2 times 1/n, 3 times 1/n, all the way up to n/n. Then we had to square them, right? Then we had to square them. And when we add them all up, we're going to have a whole bunch of values. We're going to have 1/n multiplied by 1/n squared, and we're going to have a whole bunch of complicated things in here. Okay. This is going to look ugly. So we're going to have something that look like this. Now remember, remember this point over here, the very first right endpoint that you see from the little first rectangle. This point over here. Wait, hold on. Sorry, not this one. Not this one. My bad. Okay, let's see. What time is it? Okay. So this first part over here, we want to remind you that that's the little first rectangle from 0 to 1/n. Right, so this part is 0 to 1/n. And then 1/n to 2/n, 2/n to 3/n, that kind of things. And then all the way up to n/n. Now, of course, the width over here, the width of this little rectangle over here, the width, the side, is 1/n. All of the rectangle has the width of 1/n. What's the height? The height is the y value on the right-hand side. The y value on the right-hand side is 1/n, and we're going to square that. We're going to square that over here because this is my function. The y value is x squared. If you have a different function, we will have a different thing in here. The 1/n will always be 1/n for most of your questions. You might have something else over n, depending on how big the interval is, but you'll always divide it by n. But this function part here will be a little bit different because it depends on the function. It's like the, fx plus h minus f of x, that kind of thing. It's the same idea. Once we multiply each of these rectangle out, you'll notice that each of the term will have n cubed at the bottom. You'll notice each of the term will have n cubed on the bottom. We're going to factor it out in the front. We're going to do that. We're going to take all the n cubes. We're going to factor it out in the front. Then what we are left is just the squares, right? 1 square plus 2 square plus 3 square all the way up to n square. And you can see that from here. So this is the sum of all the rectangles. And finally, we need to do a little bit more. We need to make the number of rectangle as big as we can. But before we, make the number of rectangles as big as we can. But before we do that, we need some sort of algebra to find out what this thing is. If we ever need to ask you to do this type of question on the test, you will be provided one of these charts to show you what the algebraic result is. If you're interested in finding out where these formula comes from, especially these two are sort of new. You should know this one. This is trapezoid. But if you're interested in how to find these two, you can look up appendix. It's quite interesting algebra. Now, the one that we have is 1 square plus 2 square plus 3 square all the way up to n square. That's this one over here. This means I have something square, and that something starts from 1. So 1, and then 2, and then 3, and then 4, all the way up to n. And we're going to add them all up with the sum symbol. So this means substitute 1 in here, 1 square. Right, substitute 1 in here. And then add, because this summation mark over here means to add. And we're going to keep adding until we get to n. So we're going to start with 1 square, then we do 2, we put 2 inside I, so 2 square, and then we do 3 square, okay, and then we go all the way up to the end is n, so n squared. So this tells you this particular sum is equal to dot. Once we have this, we are going to calculate the limit. We're going to calculate it. So we found what the rectangle adds up to. The rectangle, all of these rectangles adds up to become 1 over n cubed times that. And of course, we know that whole thing is equal to n times n plus 1 times 2n plus 1 over 6. So let's multiply. Oh wait, let's factor out the n. So let's factor out 1 at the end, and this is what we get. Then we're going to make the number of rectangle as many as we can. Right? Because right now we just have some rectangles. Now we want to make the rectangle as many as we can, and each of the rectangle will be so small that it's going to be a perfect line up and down that calculates the area perfectly. When you calculate the limit as it approaches infinity, look at the highest power in the denominator. So here, the highest power is n squared. So here, the highest power is square in the denominator. So we're going to multiply the top and the bottom by 1 over n squared. When I do that, the n squared goes away. These other terms will have n in the denominator, but as n becomes very big, 3 divided by a very big number is 0. So we're going to end up with 2 plus 0 plus 0 over 6. That gives us 1/3. So this is the first thing that you'll need to know. And what we have done right now is we did a big example to show you that this area underneath here, even though it's a parabola, even though the number is changing all the time, the area is a perfect 1/3. And that's sort of the beauty of integration. Eventually, we'll teach you shortcuts to get to 1/3, but for now, the definition, we're going through the definition of the integral, and the definition involves cutting my area into rectangles, adding up all the rectangles, and usually using one of these sum formulas to find out what the total is. Then we're going to apply the limit. Now we're going to pause. If we look at this question, the first thing that you need to do is find out what the width of each of the rectangle is. The width will be the length of the interval, so 2 minus -1. In this case, that will be 3. Right? The width is 3. And there are 4 rectangles in total, so 3 divided by 4 in this case. Next, we have to find the endpoints. And if I'm trying to find the right endpoints, the right endpoints are going to be written like this. So normally we will call the endpoints something like xi. You don't have to do it this way, but officially we call them xi. And the right endpoint is going to be where we start. So -1 plus I multiplied by 3/4. Now, you don't have to worry about copying this down because in 5.2, in Thursday's class, we will go through this process in a more defined manner. So we'll go through this process sort of showing you why we call this delta x, why we call this xi. We'll go through the same process. But what we are doing here is we have a interval from -1, right, to 2. And we're going to divide it into 4 different pieces, right? We're going to divide them into 4 different pieces. And in this case, we're going to use the right endpoints. We're going to call this one x1. We're going to call this one x2. We're going to call this one x3. And we're going to call this one x4. And it goes from 1 to 4 because we have 4 rectangles. This one is going to be known as x0. We're not going to use it in this case. But if we're using the left endpoints, if I'm using the left endpoints, then I will use x0 to x3. Or it might be a little bit strange depending on the notation. Actually, no, the notation will be, the notation will be a little bit strange. Yeah. So yeah, it will look a little bit different. All right, so let's not worry too much about the notation. Let's not call this x0. So this is the 4 that we're going to use. And to calculate this one, for example, the first one, for example, we're going to take -1, right? And then we're going to add 3/4. Right, that's what we do in our head. -1 plus 3/4. And the endpoint here is -1/4. Right, and what about the next one? The next one I can add from here, but I can also do -1 plus 2 of these, right? 2 times 3/4. And so that would be 2/4, or that's 1/2. So this place is 1/2. So we can do that using this formula up here, right? So this is why we sometimes eventually come up with a formula that look like this instead of finding individual one. In this particular example, it's easy enough for us to just add 3/4, add 3/4. You can even use it with a calculator, add 3/4, and that will give you 5/4. Right, so we will have the endpoints over here like these. 1, 2, 3, 4. Okay, and we know the width. We want to use the endpoint, and we want to use the endpoint with the equation here, right? We want to use the endpoint with the equation here. So we're going to, you can put everything into your calculator, or you can cheat a little. And let's see if my cheating work. Negative 1/4. I'm going to square that. Plus 3 times negative 1/4. And then plus 1. Okay, and then we're going to plus 1/2. Oh wait, I need to multiply. Okay. This might be a while. Alright, we might be sitting here for a while. So we have to multiply this by 3/4. So this is the first one. This is the first rectangle at -1/4. The y value is this part, right? Because I had to put the x value into the y value into my function to get the y value, and then I multiply by the width. Then I have to do that for every single one, right? I have to do that for the 3 other rectangles. So I can cheat a little. So let's see if I can cheat a little. I might have to erase some things here. Okay, and of course, these points here are not -1/4. They are 1/2, right? 1/2. And then this one is 5/4. 5/4, 5/4. And that one is 2. Okay, and let's see. Does this work? Oh yeah, see, so you can I don't know if you know this, but open math is very flexible as you can type a whole bunch of things in if you don't have a calculator, and it will accept the answer that way. So yeah, you can do things like this. Yeah, of course you have 2 more tries, so you can try the other ones, that kind of things. And if you don't like this question, you can always get a similar question after you finish doing all your tries. So today we're going to start with this, and then there's a second part to this. This is of course just an estimate. And if I need to find the real area underneath here, I actually need to find the sum I actually need to find the sum. And I need to do the limit. So it's a little bit different. If I need to find the real area, we're going to pretend that we have n rectangles. Now, let me see if I can clear this. Can I clear this? Let me see. Oh, I can't clear this. Okay, we're going to live with this ugly thing up here. And we're going to see if I can get around with the other part. Okay, so let's suppose we have n rectangles. Well, do I want to do that now? Okay, let's not do that now because it's going to be a messy algebra. So let's not worry too much. But if I want to find the real answer, what I'll do is I'll say I have n rectangles. The width will be something like the width will be, in this case, delta x will be 3/n. 3 because it's 2 minus -1. The distance is 3. And then each of the endpoint will look like this, but not have 3/4. It will have 3/n. And what we will have to do is we will then have to substitute this into our formula and get a very ugly algebraic thing. Okay, so we're going to have to do that and then do the limit. So it's a little bit of an ugly thing, and we're only going to do that with very simple examples. Okay, let's go back to our notes for a little bit. Now, before we go on, for the assignment 1, you can, after today's lessons, you can try the first 4 questions. You can try the first 4 questions in here. And you might get stuck somewhere, but just ask when you come to class on Thursday. Okay, let's go back into our notes and let's continue on a little bit. And we're just going to clear up a few more things. So what we should realize is that if I don't have a lot of rectangles, the estimate is not very good. And when I have more and more rectangles, you'll notice that the estimate here is better and better. How do I know it's better? The gap that we have, or the excess, or the extra part that we have is getting smaller and smaller. And you'll notice that whether I do it with the left end, whether I do it with the right endpoints or the left endpoints, as the number of rectangle becomes more and more, the answer will be equal, right? These 2 pictures, the area look very similar. And if I have even more rectangles, they will eventually be the same. So the area, so we define the area. So the real definition of the area is to break my area into these little rectangles and make the rectangle as small as we can and have as many rectangles as we can. So we're going to look at each of these little rectangles, either using the right side or the left endpoints, and we're going to make the number of rectangles as many as we can. So we're going to do the limit. Each of the small rectangle contains 2 parts, the width multiplied by the height, and the height is the y value. And we don't have to only use the right endpoint or the left endpoint. We can pick any point in between. So you'll notice that here, I draw my rectangle and I just pick, or the textbook draw its rectangle, picking sort of all sorts of strange points. And these sample points, they use the star to represent it. So in the first interval, they sampled at somewhere close to the left-hand side. They call that point x1 star. And then in the second interval, they do it in the middle. In the third interval, they do it on the right-hand side. They do it at different points of the interval. But the area, as the number of rectangle approaches infinity, is going to be the same. Okay? If I make the rectangle very small, it would not have mattered. So this is the definition of area, and this is the definition of what we're going to be doing in integration. The last thing that we want to share today is the distance problem. And we want to show you that the distance, finding the distance, is really the same thing as finding the area. It's the same process. So you know that calculus is developed by mathematicians, and the most prominent one, Isaac Newton, he's a physicist as well. So one of the things that people were trying to do was one of the application of calculus is to use it to work with physics, whether to calculate distance, velocity, force, all sorts of things. And so distance is one of them. To find distance, we take the velocity, we take the speed multiplied by the time. But let's say we're driving, and when we're driving at different speed, right? At the beginning, I'm not going very fast, but 5 seconds later, the traffic was good and my car speeds up. And then after a while, I realize I'm going a little bit too fast. There's a police car in the front, so I start to slow down a little bit. If we need to estimate the distance, then it's sort of like these are the velocity. I want to multiply by time. Each of these interval is 5 seconds. So I might want to take the velocity times 5, velocity times 5. I might want to do something like that. So we can do the same thing using the left endpoints in this case. So what I have is something like that. My velocity can be going at a different speed. But I know I started from 25 and then it goes up to 31 and then 35 and then 43, 47, 45, and it comes down to 41. If I use the left-hand point, I end up having similar situation. Because here we're multiplying things, right? We're multiplying velocity with time. And one of the things that you have to realize is that when we are multiplying things, and in this case, the velocity can be changing. If I'm multiplying things, multiplying two values, and one of the value is changing, that's okay. We can still find the product. We can still find the product. Or we can find the area in this case. And we do integration. It's the same process, cutting them into rectangle, making the rectangle as small as possible. So that's what we are saying down here. If I make this rectangle as small as we can find the actual distance. And in Chinese, in Mandarin, the name for integration is the same as the name for product. Because if you think about it, the word 基数, it means product. It means two things multiplied together. So here, velocity, we're taking velocity times time. We're multiplying these things together. And that's the first important thing that you need to